Hi everyone, I'm Lauren.
And my name is Christian.
And today we're going to be teaching you about molecular orbital theory. We've selected a problem from our course reader, and so let's get started. The problem says, nitric oxide is also called nitrogen oxide and is an important cellular signaling molecule. Draw the valence molecular orbital energy diagram for NO and label all of the orbitals. So, as you can see, this is our molecular orbital diagram. To the left, we have an arrow pointing upwards that shows that energy is increasing as we move up this diagram. To the left right here, we have our atomic orbital with an N that represents nitrogen, and to the right, our second atomic orbital with an O that represents oxygen. So I already labeled our energy levels, but let's begin by filling out our atomic orbital levels. So first we are going to start with the 2s, and nitrogen has 5 valence electrons. So I'm going to start by filling out 1, 2, 3, 4, 5. And we have to fill each orbital first before we pair them, just because of what is known as Hund's rule. Next, we're going to fill the oxygen. So oxygen has 6 valence electrons, so we're going to start with 1, 2, 3, 4, 5, 6. And the same rule applies here, Hund's rule, which is why we fill the three orbitals first, and then this is the only one that is paired. Because nitrogen and oxygen both have valence electrons that are less than 8 valence electrons, we use this version of the molecular orbital diagram. If our Z number was greater than 8, the sigma 2pz orbital would be lower in energy and it would come down here. But this is our diagram for this particular problem. So now we're going to start filling out our molecular orbitals, and to do this we have to just take the sum of the valence electrons for nitrogen and the sum of the valence electrons for oxygen, and that total is 11 valence electrons. So we're going to start by filling out the sigma 2s level. So 1, 2, moving on to the sigma 2s antibonding level, 3, 4, pi 2p, sorry, pi 2px, that's our 5th valence electron, and then our 6th valence electron in the pi 2py, 7th, 8th, 9th, 10th in the sigma 2pz, and our last valence electron will go into the pi antibonding 2px orbital. So this is our molecular orbital diagram completely filled out. This is for the valence electrons, by the way. And now we're going to do the electron configuration. So our electron configuration will be sigma 2s with a superscript of 2 to represent the 2 electrons, sigma 2s star for the 2 electrons and antibonding. And then I'm going to combine these 2 orbitals in the pi 2p with 4 valence electrons, and then sigma 2pz with 2 valence electrons, and finally our last one is pi antibonding 2px with only 1 valence electron. And that is your electron configuration. Good, Christian?
Okay. So now what I'm going to do is go over bond order. And pretty much all it is we are going to first take the bonding molecular orbital, which is pretty much all of the ones that don't have a star next to it. And we're going to count them up. So first we're going to go to the sigma bonding molecular orbital, 1, 2 here. Then we're going to go up to the pi, 3, 4, 5, 6, and last but not least, the other sigma, 7, 8. 2, 3, 4, 5, 6, 7, 8, right. And we're going to subtract, and now we're going to count up all of the anti-bonding molecular orbitals, 1, 2, and 3 here. Again, the anti-bonding are the ones that have the star next to it. And all we're going to do is take the 8, subtract it by 3, and divide by 2. We divide by 2 simply because that's what the formula says. So now when we do 8 minus 3, we're going to get a 5 here. And again, we're going to be dividing by 2. And a more simplified version than that, 5 divided by 2 is 2.5. And that is the bond order for this particular molecular diagram. Okay, now we're going to go over to Paulina.
Hi, I'm Paulina, and what I'm going to go over is paramagnetic and diamagnetic. So right here, this molecular orbital is paramagnetic because that's what it means is that it has an unpaired electron, which is right here. It doesn't have a pair such as these do. And it would be diamagnetic if this didn't exist and they were all paired like this, but since it's not paired, it's paramagnetic. So then you write down it's paramagnetic. And then also some other questions you can get for it were, is it homo, like what are the homos and lumos of it? So the HOMO of this would be highest occupied molecular orbital. So the HOMO would be the highest occupied one is pi star 2p. So that's the pi 2p antibonding. So your HOMO would be pi star 2p. And your LUMO, it means lowest unoccupied molecular orbital. So that would be your sigma star 2p. So right here you'd write LUMO, sigma star 2p. And those are all the questions you could get from molecular orbital theory. Thank you for watching.